Think about multiplication. If I show you this equation, do you think it's true? Obviously, right? How about this one? Who even writes parentheses? One more. This must be some kind of joke, right?
How about this?
I said to think about multiplication, but I never said to think about multiplication with numbers. In mathematics, the structure of multiplication is usually expected to satisfy the first two equations, but the third one is not a given. A multiplication which satisfies this third equation is said to be commutative. Both integers and matrices have the structure of a multiplication, but you could say that integer multiplication satisfies more properties than the matrix multiplication. What, think property is theft or something? We can say the exact same thing by instead counting how many multiplications the integers have compared to matrices. Matrices have the one multiplication, but integers have two. I know what you're thinking. What the heck is G talking about? If that's not what you're thinking, don't worry. That'll be fixed later in the video. Somehow, I'm claiming that a commutative multiplication is the same thing as having two multiplications. We've known about integer multiplication since grade school, so what is this mysterious twin earth multiplication then? Instead of answering this question, let's address the opposite question first. How does having two multiplications give us commutativity? Let's suppose we have two different multiplications that are independent of each other. Maybe this isn't the easiest thing to conceptualize. In mathematics, or maybe just my neck of the woods, multiplication is usually assumed to be associative and unital, but it's not generally assumed to be commutative. And the reason is because mathematicians tend to think of multiplication as a kind of composition, rather than honest-to-goodness scalar multiplication. This includes stuff like function composition, matrix multiplication, which is just function composition, and concatenation, which is kind of still just function composition. In all of these cases, you don't generally expect that reversing the order of the factors would give you the same result. Therefore, when I say, think of two independent multiplications, maybe it'd be better to instead hear that as, think of two independent compositions. This can also help us understand what it should mean for two multiplications to be independent of each other. Suppose I have four quantities arranged in a square like this. Then, there are two different ways I can compose this arrangement together. I could either compose horizontally and then compose the results vertically, or I could do it the other way and compose vertically first and then compose the results horizontally. If these multiplications were truly independent of each other, then both of these processes should yield the same result. Now, remember back in physics class how you were always told to remember your units? Well, this isn't really the same thing, but we also need to remember our units. If you're not really physicsy, I know what you're thinking. 2 units, that's far too many. Luckily for us, the 2 units are actually equal, so we really only have to remember 1 unit, and this unit works for both multiplications. This is interesting. Despite these multiplications being supposedly independent of each other, they share the same unit. I wonder how else these multiplications are related. Anyway, using the shared unit, we can finally show that horizontal multiplication is commutative. What about vertical multiplication? Oh, it's commutative too. This is because the vertical multiplication is actually exactly equal to the horizontal multiplication. That's right, the mysterious parallel universe multiplication of integers is actually just the ordinary multiplication of integers. This cute little hoodwink is called the Ekman-Hilton argument. But gee, you might be thinking, who cares? That's a T5 question. For what it's worth, I obviously care about this, but more broadly, topologists care about this as well. Topology is, speaking reductively, the study of shapes. But that's actually pretty hard to do. Even just telling shapes apart is hard. There are many cases in a math department where the house topologist bites into a mug or drinks coffee out of a donut. Rather than investing in better pairs of glasses, though, topologists look to algebra for help. After all, glasses and eye exams are expensive, but algebras are sometimes free. Through algebra, topologists found that they could associate groups with these shapes, which is something that allows you to multiply, like we've talked about already, but also divide. These groups couldn't tell the mug and the donut apart, but they could finally tell the donut apart from a Timbit. This was such a monumental achievement that they named these groups fundamental groups. I'm not here to give a crash course on the foundations of homotopy theory, but to give a bit of context, fixing some space and a chosen base point, the fundamental group consists of all continuous paths from the base point back to itself. Academic regulations require me to mention that you're allowed to continuously deform these paths without changing the corresponding element of the fundamental group, so long as these paths keep the endpoints fixed throughout the transformation. Anyway, you might have been able to guess, but the multiplication in a fundamental group comes from concatenating paths tail to tip. In particular, the midpoint is no longer constrained to the base point, which is what allows for interesting structure here. If you're curious, the corresponding division comes from concatenating one path with the reversal of the other. If you haven't been in the trenches of topology, these fundamental groups might seem pretty benign. But every group can be realized as the fundamental group of some pointed space. You might be wondering what this has to do with multiple multiplications. Well, it wouldn't be topology if we didn't try to increase the dimensions somehow. You might have noticed that there is a 1 in the symbol for the fundamental group. This 1 refers to the fact that lines are one-dimensional. If we replace these lines with squares and require that the entire boundary of a square has to remain fixed at the base point, then we get pi2, the second homotopy group. Pi2 can also be endowed with the structure of a group, and the idea is to again use concatenation. But in this case, there's a bit of an ambiguity for how the concatenation should go. The two natural candidates for multiplication are to compose these squares horizontally or vertically. Luckily for us, the Ekman-Hilton argument already tells us that it doesn't matter which choice we make, as either way we get the exact same structure. The catch, though, is that the multiplication is then necessarily commutative. That is, pi2 is always a so-called abelian group. As a result, although any group can be realized as the fundamental group of some space, only the abelian groups can be realized as higher homotopy groups. I know I baited you into thinking that two multiplications on integers are different, but I know this tidbit of algebraic topology makes up for it. If you disagree with that, it's okay. I'm in no position to make you feel bad for being wrong. You might be wondering what Ekman and Hilton have to say about pi3, where we probe our spaces with cubes instead of squares. In this situation, we can still define a perfectly good group, but now there are 3 candidates for the multiplication. What does this mean? Is pi3 more commutative than pi2? How can the equation for commutativity be satisfied more strongly? Well, whenever you're in the situation where some things are more equal than others, you might need categorification. When you have a set equipped with a multiplication that is associative and unital, you get what is called a monoid, or, as nobody calls it, a monoidal set. The vertical categorification of this concept is what's called a monoidal category. In the unlikely case that you're not familiar with categorification, the process basically amounts to replacing sets with categories, functions with functors, equations with natural isomorphisms, and then you add some magical coherence diagrams. This means that a monoidal category is a category equipped with a multiplication functor, a unit object, and what used to be associativity and unitality categorify to natural isomorphism data called associators and unitors. Then, these natural isomorphisms are subject to coherence axioms, which I've written up in LaTeX way too many times in my life. What you might notice with this procedure is that things that used to be given by properties are now upgraded to natural isomorphism structure, and this structure is now subject to new properties that we haven't seen before. In particular, different choices of associators give us technically different monoidal categories. The same will be true for commutativity. it's not just something that is either true or false for multiplication, but instead it's exhibited by an explicitly chosen natural isomorphism. You're probably hoping for an example of a monoidal category. I could go ahead and give you the prototypical example, or give you the lazy example, but since I like you so much for sticking around this long, I'm going to give you a super example. The objects of my example are going to be given by complex vector spaces, but not just any vector spaces. These are super vector spaces, where each vector can be decomposed uniquely into a bosonic part and a fermionic part. If those words don't mean anything to you, that's good. They don't mean anything to me either. They're just cool sounding labels for things that make this example extra super. A result of this Bose-Fermi decomposition of vectors is that the vector space itself also decomposes uniquely into its bosonic and fermionic parts. The maps between objects in this category are given by linear transformations that respect this decomposition of the vector spaces. So far, we've only defined a category. The monoidal structure on this category is given by the usual tensor product of vector spaces. To make this tensor product super, we say that the tensor product of two bosonic vectors or two fermionic vectors would both give us something bosonic, and on the other hand, the tensor product of a bosonic vector and a fermionic vector is always fermionic. In this case, the tensor unit is the superspace generated by a single bosonic vector, but I'll leave it to you to figure out what the natural choice of uniters is. To show that this tensor product is associative, I need to write down natural isomorphisms between the two ways we can compute U tensor V tensor W. As we can see, the vectors in these threefold tensor products look pretty similar, but they're not the same, so the associator is a bit more interesting than the do-nothing identity map. That being said, it's not terribly deep. Now, if I were to tell you that this tensor product is also commutative, I would similarly have to exhibit this with a kind of natural isomorphism beta that swaps the order of superspaces. Of course, such a natural isomorphism would also have to satisfy its own coherence rules, called hexagon axioms. Yeah, category theorists are not known to be the most original when it comes to naming these things. Confused? As I learned in my graduate teaching and learning program, a picture is worth 1,000 words. So here's a 32 by 32 8-bit uncompressed bitmap of a hexagon. If we extend our mental picture of multiplication as concatenation, we can think of the tensor product of arrows as putting threads side by side. In this presentation, our commutativity can be drawn as crossing one thread over the other. Accordingly, the natural isomorphism beta is called a braiding, and providing a braiding gives us a braided monoidal category, which is the categorification of a commutative monoid. Or is it? For reasons I will probably never spell out in my life, the Ekman-Hilton argument categorifies to show that a category with two compatible tensor products is the same thing as a braided monoidal category. This makes the braiding a promising candidate for a categorified commutativity. But note this. What happens if I braid twice? Braiding twice means swapping V with W and then swapping back. But this picture of a double braid makes it seem like the end result is something more than if I had just done nothing to begin with. This is a precursor to using objects of a braided monoidal category as non-invariants. If we look back at our super example of a monoidal category, we can upgrade it to a braided monoidal category in many ways. Here's one that's probably in Euler's imagination. To identify the superspace V tensor W with W tensor V, follow this recipe. Given a pure tensor of a boson in V with a boson in W, just swap them. Given a pure tensor of a boson in V and a fermion in W, just swap them. Given a pure tensor of a fermion in V and a boson in W, just swap them. Given a pure tensor of a fermion in V and a fermion in W, just swap them. And multiply by e to the I. Everything else is just a linear combination of these rules. With this mapping, you can check that this makes our category of superspaces into a braided monoidal category. Moreover, we can see that braiding twice is not the same as doing nothing. If both factors are fermionic, then the double braid rotates the resulting tensor by 2 radians. In fact, no matter how many times you braid, you'll never end up undoing anything. This isn't actually good if you're interested in commutativity though. Commutativity is supposed to reflect an insensitivity to reordering, but this phase shift of 2 radians for swapping twice suggests that braiding still has some sensitivity to reordering. If we strengthen the axioms of a braiding to insist that the double braid does nothing, we arrive at a symmetric monoidal category. This is the answer to our question about what happens when you have 3 compatible multiplications. Having 3 compatible tensor products is equivalent to having a symmetric tensor product. By choosing a different braiding, we can make our super example into a symmetric monoidal category. Specifically, instead of having swapped fermions pick up a multiplication factor of e to the I, we can just negate it. Since -1 squared is just 1, this defines a symmetric braiding. In the literature, this symmetry also goes by the name of Susy. Now I know what you're thinking. What about 4 multiplications? Well, my Chinese heritage forbids me from talking about 4s. Luckily for me, I'm only half Chinese, and adding a 4th multiplication doesn't do anything anyway. A symmetric tensor product is as commutative as a tensor product can get over categories. But as you might predict, a 4th tensor product has tangible effects if we categorify further and talk about monoidal 2 categories. If you don't know what a 2 category is, in a set, you just have elements. In a category, you have elements, and between 2 elements, you have a set of arrows. In a 2 category, you have elements, and between 2 elements, you have a category of arrows. In any case, though, I don't really want to talk about monoidal 2 categories. From our extended table of multiplication, there are a couple of natural observations to be made. First, what the heck does sylleptic mean? Secondly, there's a pattern with how commutativity stabilizes at each categorical dimension. Specifically, one step of categorification allows for 1 more multiplication to strengthen the commutativity of the operation. This observation is called the stabilization hypothesis because, hypothetically, if I were a tensor product and you were a k-tuply monoidal n category, would you commute more to see me, or is k at least n plus 2? Naturally, with all this talk about higher categories, it would be a sin to not talk about infinity categories, just as it would be a sin to have a channel called the sheafification of G and never talk about sheafification. In the infinity categorical setting, adding a new compatible tensor product always strictly strengthens the commutativity of the multiplication, and it never stabilizes. In particular, none of these rows serve as the infinity categorical analog of true commutativity. Instead, you need infinitely many multiplications to achieve true symmetry. This picture here is essentially the periodic table of k-tuply monoidal n categories. Of course, this table is given its name because of its similarities with the periodic table of finite simple groups. If you've made it this far, tell me your favorite finite simple group. Mine is the finite simple group of order 2. If you're still here, thank you for watching. If you liked what you watched, there's a -1 categorical object that can demonstrate this. If you didn't like what you watched, it's probably because you never thought, what the heck is G talking about, like I promised you would. If that's the case, you might want to rewatch the video. If my track record means anything, you'll find some humiliating error in the video, which will leave you wondering, what the heck is G talking about, like I promised all along. If, even after this, you still didn't like what you watched, twice, it's fine. You may be able to infinitely decategorify the collection of fans who've got my back, but this is precisely because the only infinitely decategorifiable object is inhabited.